Hi, I'm LOK from Group 6. I'm the measure presenter for the erosions and sedimentation plan. Now we move to the introduction. The uncontrolled erosion of soil and the sedimentation in the construction area will definitely cause water pollution and affect water quality of a number of water courses and receiving water due to severe siltation. The soil eroded and the sedimentation loss will need to be deposited and treated in one place, thus the flow of water out of the construction area will not cause water pollution. Now we move on to the layout of the plan. So the figure below shows our final proposed design of the ESCP in the site area. I have differentiated it into three parts, which is camera area A, B, and C according to the proposed design level from the earthwork group. So it does not place at the same level as we design it, so it will not cause the problem. And we have the design the temporary drainage system for each catchment area there, and then we have the sediment basin, total 3, and a wash bay, and we have 2 entrances, so the system are flow well to the outlet there. For runoff management BMPs, for dealing with the stormwater runoff, the temporary earth drain is implemented and the drainage site is designed to achieve optimum flow and reduce soil erosion and sedimentation risks. So first one, we get into the project design, the rainfall estimation. The rainfall estimation involves frequency, duration, and intensity analysis of rainfall data. The parameter need to be considered is the RI. RI is the rainfall and subsequent discharge estimate, which based on the selected frequency or return period. So we use 2 years as we assume it at the early stage of construction work will be completed within 2 years. The second one is time of concentration, which is the travel time of runoff flow from the most hydrologically remote point upstream in the contributing catchment area to the point under the consideration of downstream. So this is the formula: TC equal to T0 plus TD. T0 equal to 107 times N times L power per 3 and divide with the S power of 1 per 5, and the TD is the L over V. So where the TC, we can say the time of the concentrations, T0 overland sheet flow travel, TD is drainage flow travels time, L length of the overland sheet flow, N is Horden roughness value, S is slope of the overland surface, and L length of drainage flow, and V is the velocity of flow. This is the average rainfall intensity, where this is the formula: I equal to average rainfall intensity, T equal to average recurrence interval, ARI, and D is the storm duration, and this is the fitting constant depend on the rain gauge, which is the lambda, K, data, and N. We move to the peak discharge flow estimation. The whole construction site has been divided into a few small catchment area and also divided into few sub-catchment area for each drainage. So we use the Q peak for each drainage to calculate. The Q is peak flow, C is the runoff coefficient, I average rainfall intensity, and A equal to drainage area. This is the sub-catchment area from the catchment area as we analyze it into the 3 parts. Now we move on to the calculation of the rainfall estimations, the example. So we need to know the concentration of TC, we need to have the T0 data. So how to get T0? We need to have the L length of the overland sheet flow, and the N we equal to best slope, and S equal to slope of the overland surface. The length of the overland sheet flow and the slope we can gotten from the plan layout and we analyze it. So we substitute all the value these 3 inside, so we get the 8.298 means for T0. To know the TD value, we need to have the length of the drainage and also the velocity of the flow. So the length of drainage is this, and how to get the velocity of flow? So we need assume the drainage. So the depth of the channel is assumed 0.3 meter and width is 0.5. So we get the area here and perimeter and R. So we substitute, and the S0 also we get from the slope of the temporary drainage. We substitute all the value inside to get the velocity, and with the velocity we have the length, then we have the TD, then we can get the TC by plusing the T0 with TD. In order to know the peak discharge estimation, which we need the average rainfall intensity I value. So according to IDF constant, since it is near to the Pergananas as Ulu Tilam, so we use it lambda equal to 54.265, K equal to 0.179, data equal to 0.1, and N equal to 0.756. Apply all the data inside the I, we get 176.386. So we substitute the value inside to get the Q equal to 0.457 meter cube per second. This is the table of all the result analyzed. So we can see that this first table, this one is actually from all the catchment area and all the drainage. So all the TC has been analyzed using the method I mentioned just now. We get all the TC, then we use the TC here to substitute inside. You can see in the table too, all the TC here. We can get the Q peak from all the TC and the I value we get. So this is all the analyzation. Now we move to the temporary drainage. The design of temporary drainage for our project is use trapezoidal shaped open channel as reference. We assume that the trapezoidal shaped open channel is able to cater the flow of the water. It is able to cater larger water flow compared to rectangular and triangular shaped channel. The trapezoidal section we use has a size slope of 1.5 to 1, and we also use the Manning equation to calculate it. Now we move to the design drainage for catchment area. So we need the Manning volume Q, so we need the A and V velocity. So from the velocity we need the parameter of the R and also the S0. So S0 we get from the layout there as we propose the drainage there, we got the slope, and then we assume the depth y equal to 0.4 and b equal to 0.5. We substitute the value inside to get the T, the length above there, the water level, A area, and then we have the perimeter. So from there we area over perimeter, we get the R, we have the R, we get the V value, then we can times with the area to get Q capacity equal to 1.943 meter cube per second, which is larger than Q peak as just now, so it's able to cater the peak flow. This is a table analysis of all the designs of all the temporary drainage. So from the formula just now and the similar method applied, we can get the Q capacity for all the drainage. This is a long section of example of temporary drainage to prove that the connections between the sediment basin and also the proposed drainage is connect, so it does not below the level of the sediment basin. Now we move to sediment control BMPs. Construction activity is the most common source of sediment pollution. Sediments are the most common pollutant found in the rivers, streams, lakes, and reservoirs. Sediment control is the practice or structure that is designed to keep eroded soil from the construction site so that it does not wash off and cause pollution to the nearby waterway. The structure is usually located at the downstream of the construction site, such as sediment tract and sediment basin, to track the excessive sediment produced. Now we move to soil loss estimation. So the universal soil erosion equation will be used to assess the erosion risk of the site under the conditions such as the condition of existing, undisturbed, disturbed and uncontrolled, and disturbed but controlled. So the most widely used formula is A equal to RK/LSCP, where A is the average annual soil erosion loss, R is the rainfall erosivity factor, K equal to soil erodibility factor, and LS is the topographic factor that represents the slope length and the slope stiffness, C cover management factor, and P is support practice factor. So from the previous formula, we need to know the rainfall erosivity R factor. So from this map, we can assume that the location is Ulu Tiram and R value in range of 14,000 to 15,000. Then for evaluation purpose, we choose the value R to be 14,000 as is stated in the Ulu Tiram. And then we go to the soil erodibility K factor. So this is the particle size distribution given for the three designated zone. And then we got the structural chord and permeability chord. And then for designated zone A, we get the K factor 0.035, B is 0.039, and C is 0.037, which shows that the A is sandy loam, B is loam, and C is loam. So to get the LS factor, the horizontal slope length and the slope thickness needs to be determined through the elevation information available on the site. So there are the three conditions which are existing: earthwork, uncontrolled, and earthwork control from the control of the topography map. So there is the different one. So we refer to the table for the slope stiffness and also the slope length. If we cannot find it inside the table, we use this formula to get the LS factor. For existing slope, I take the catchment area A as the example. So we identify the horizontal slope length of at the catchment area A, and then we measure the length of it. So from there, the highest point and the lowest point of the horizontal slope will be used to calculate the slope stiffness. So the elevation will be taken from the existing contour map. So we get it is 10.395%, and we substitute it into the formula to get the LS factor of 4.571. Similar to catchment area B also, we analyze the length at the catchment area B for the horizontal slope length, and then we get the elevation from the existing contour map. We get the 7.65%. We apply it into the LS factor formula to get 2.394. Similar with the catchment area C, we analyze the length, the horizontal slope length, and then from there we also use the existing contour map to get the elevation. From the highest to lowest, we minus difference it, and then we get the percentage, and then we apply it. We get the LS factor is 0.452. For earthwork, uncontrolled, and control, we use the similar method as just now I mentioned at the existing, but the difference is the slope stiffness. So we use, as the same plane, we use the design platform level as the elevation. The difference between it, we apply it to LS factor, and we will get the different LS factor with the existing one. But the earthwork uncontrolled and controlled will be the same. Now with determinations of C factor and CP factor and soil loss. The determination of C factor: for the undisturbed condition, the entire site covered with 95% forest coverage, and then the C factor is 0.03. For earthwork uncontrolled, C factor equal to 1, and for earthwork control, C factor equal to 0.5. The determination of the CP factor: for existing condition, no management support practice is provided, so it is undisturbed site and also the earthwork control. Therefore, P factor is 1.0, and therefore earthwork uncontrolled is 0.5. So we substitute all the value inside to get the soil loss. Estimations of soil loss from catchment area A can be determined as the 65.114 ton per hectare per year. This is the analysis, the results of all the soil loss of the area by the formula just now. To all the existing earthwork uncontrolled and earthwork control, we get all the soil loss at the end. Now we move to the sediment yield estimation. Sediment yield is the amount of sediment expected at the end of the drainage point from the designated site. Therefore, this estimation is used to predict the amount of sediment for sizing and maintenance of sediment control BMPs. The MUSLE is normally used in the estimation of sediment yield of a catchment area as a result of a specific storm event. The estimated amount of sediment storage volume is used in sediment basin. This is the formula that we use to estimate the sediment yield per storm event. The calculation of sediment yield estimation: the designated storm equal to rainfall intensity times storm duration, and we get the design storm is 30 mm. Catchment area A equal to 11.24 hectare. Time of concentration TC equal to 11.452 min, which is the highest TC that we have analyzed at previous. And then we get the intensity of the design storm from the TC. The calculate peak discharge: we use the value inside, we substitute, and we get the 2.439 meter cube per second. Now we calculate the runoff volume. We use the rational method, hydrograph method, with the time concentration TC equal to 11.452 min. Then we substitute all the value inside, and we get the Y equal to 310.776 tons. Followed by catchment area B and C, we have the TC and intensity of density of each area. Then we analyze it into the table. For the basin A and BC, we use the formula just now. We get the Y for each of the basin A, B, and C. Now we move on to the design of sediment basin. We take the sediment basin 1 as the example, and then type of sediment basin we use is the dry sediment basin as is. Assumed as the sandy loam due to the soil distribution just now. Then the basin dimension: the required surface area is 200 meter square per hectare. The required total volume is 240 meter cube per hectare. So the catchment area is 11.24 hectare. So the surface area, the multiplication between the 11.24 and 200 to get 2,248 meter square, and total basin volume is 2,697.6 meter cube. The required settling zone equal to 1,348.8 meter cube, half of the total volume, and then the selected settling zone equal to 0.6 meter, which is the minimum one. Try settling zone average width we use 35, and then the settling zone average length we use 75 as we calculation from 64.23 we assume it to be 75, and then the average surface area, the multiplication between this 35 and 75 we get 2,625 meters square. Checking settling zone, we get the first one is 125 meters, smaller than 200, and then the second one is 2.14 meters, larger than 2, so it's okay for the settling zone. Now we move to sediment storage zone. The required sediment storage zone is 1,348.8 cm. For the side slope we use 2 to 1, and then we get the width is 33.8, the length is 73.8. We use the formula to get the Y2. The Y2 we get is 0.57, so we assume it to be 0.6, which is larger than 0.3. The volume is 1,420.056, larger than 1,348.8, so it is assumed to be okay for the design for sediment storage zone. Now we move on to the overall basin dimension. At the top of the water level is about 33.8 meter, the length is 73.8 meter, and at the base, which is the bottom of the water level, the 31.4 meter and the 71.4 meter. So now we move to the sizings of basin outlet. The spillway for the sediment basin must be designed for 10 years ARI, and the proposed spillway dimension is about 1.5 meter wide times 1.2 meter. Then the spill level must be set as minimum 300 mm above the basin top water level. To simplify the calculation, the following assumptions are made. So we use determinations of Q10. Now we substitute all the value inside. The storm duration is how to get. We use the TC just now, then we put in all the value and we get I equal to 208.415 millimeter per hour, and then we get the Q10. Now with the determination of Q riser, we try with one orifice with dimension 0.7 meter at the stem level, and we allow the head of the 1.2 meter from centroid of orifice. So we get the Q riser is 1.12 meter cube per second. Now we go to sizing of spillway. The trial dimension B equal to 1.5 meter and the HP equal to 1.2 meter and SCP equal to 1.49 from table, and then the Q required is 3.254 minus 1.12, and we get 2.134 meter cube per second. The Q spillway we get is 2.938 meter cube per second, is larger than the 2.134, so it's okay for design. So the whole total basin depth including the spillway is 2.7 meter. Then from there, now we go to trapping efficiency. So the sediment use estimation, just now we assume it at the first is 310.776 tons. Now the efficiency is about 90%, so we get 279.698 tons or 153.849 meter cube. Now we got as long as the volume is larger than the total sediment yield trapped, so hence the provided sediment basin is able to occupy the settled sediment. Now this is all the designs of the basin 2 and 3. All the calculations are inside and all are adequate after the calculation of all. This is sizing of the basin outlet and trapping efficiency. The plan view, the section view, and also downstream elevation has been drawn for the sediment basin. All the dimension is displayed on the drawing, and then all the dimension here at the side of the table will be used for the drawing for here. For erosion control BMPs, first is FUNG. FUNG is a temporary sediment barrier made of porous fabric that are made for the trapping seed and sediment from disturbed area during the construction phase. It is held by the wooden or metal post driven into the ground, so it is actually inexpensive and relatively easy to remove. This measure does not filter runoff, but it acts as a barrier that traps and intercepting the sediments from disturbed area in order to accumulate them from entering the stream beside, reducing the velocity of runoff flow. In our project, the steel fences are placed along the low elevation location. The second is wash throw. During the land clearing activity and the movement of various vehicles on the site, the dust dispersion from those activities will significantly affect the quality of air and water. Therefore, dust prevention should be exercised for all the FO operation. One of the applicable ways for dust prevention is the installing wash throw at the site. A wash throw is an area located at stabilizing construction access exit points to remove sediment from tires, undercarriages, and even the body of the machinery that leaving the site. Any machine leaving the construction are required to undergo washing process at the wash throw. So the washing including the thorough washing from the mud and salt. 3 wash beds are applied in our project site. The third one is seeding and planting. Seeding of grass and planting of tree, shrub, and ground covers provide long-term stabilization of soil. It is suitable during and after construction in any graded or cleared area where construction activities have ceased. Open space, cut and fill areas, steep slopes, spoils, stockpile, vegetated swells, landscape corridors, and stream banks. The fourth one is stockpile. A stockpile is a pile or storage location for the bulk materials, forming part of the bulk materials handling process. There are 3 top piles that are applied in our project site. Now we move to conclusion. The project site has been undergone the soil erosion and sedimentation control to prevent the possible pollution when the earthwork project is going on. All the design, the temporary drainage and sediment basins are provided from the project site. The objective of the soil erosion and sedimentation control plan has been achieved. That's all for today. Thank you.